Okay, so we're going to be drawing a bunch of pictures for SI2 here. So there's going to be three different cases. In each case, there's two surfaces given. Those are oriented surfaces that have the same boundary, and therefore their difference is the boundary of some solid region, and we just want to describe what that region is and be careful about the orientations. So we'll just do these one at a time. Let's first talk about number one here. So S1 is the upper half of the unit sphere oriented upward. So there's our S1. Right. S2 is the lower half of the unit sphere oriented again upward. Now, again, this is S2. So keep in mind, these look like opposite orientations because that's outward, that's inward, but they're the same in the sense that they put the same orientation on this boundary curve. Right, they both orient the boundary curve that way. Does that make sense? Okay. So now the question is, let me go back to the statement here. S1 minus S2 is the boundary of some solid region. So we want to think about S1 minus S2 and what solid has that as its boundary. Okay, back to the picture. So, let's try to draw a picture of S1 minus S2. Well, S1 minus S2 is going to look a lot like that. It's just S1, so it's that up there. And now minus S2 looks a lot like S2. It's the bottom half of the sphere, but it has the opposite orientation from S2. S2 is oriented that way. That means that minus S2 is oriented that way. And the question is this difference, so is that S1 minus S2, is that the boundary of some solid? And I claim that it is. In fact, this is just the outward oriented unit sphere at this point. That's the boundary of the unit ball. Does that make sense?
So the S are just surfaces.
Yeah,
right.
That's right.
But is B a solid then?
B is a solid. B is the solid ball, the three-dimensional solid ball. Yeah.
Do the surfaces have any thickness?
Nope. There's two-dimensional surfaces.
All right.
Yep. Is this all good?
Yeah, that makes sense.
Okay. Let's look at part 2 here then. So part 2, let's see here. Upper half of the unit sphere oriented downward. S2 is the unit disk in the XY plane oriented downward. All right. Okay, so let's see number 2. So here's S2 is the upper half of the unit sphere oriented downward. And S2, that's S1. S2 is this disk here, also oriented downward. That's S2. Right? That's our picture. Everybody happy? Okay. So now again, we want to try to figure out what does S1 minus S2 look like. That's what the problem asks us to do. Well, S1 minus S2 is going to look very similar. S1, still there, like that. Now, minus S2 looks a lot like S2. It's the same actual set, but with the opposite orientation. That's going to then be oriented like that. That's your minus S2. Does that make sense?
Why do we choose to orient S2 inwards instead of S1
So
upwards?
So S2 by the given S2, if you look at in the statement of the problem, S2 is the unit disk oriented downward. So this is given to be the orientation of S2.
Oh,
that's given.
S2 is the unit disk.
Yeah. That's because we're on the second part of the problem now. Yeah, exactly. So S2 is given downward. That means minus S2 is oriented upward.
Right.
Okay, so this is what we're looking at. This is our S1 minus S2, and we have to ask, is that S1 minus S2 the boundary of something, and I claim that it is, and we got to be a little bit careful here. It's tempting to say, well, let's just look at the solid region, and that's sort of, capped off by these two surfaces, and that, get that region R. The problem is that region R, the boundary of R is actually, I'm going to have to draw another little picture here. If R is on the inside there, the boundary of R has to be oriented outward like so. This is how the boundary of R is oriented.
Right.
So set-wise, yeah, the boundary of R is, S1 and S2, but with the orientations as we have them written here,
Negative.
yeah, both of these orientations are the exact opposite of what the boundary of R's orientations are. So R is not the right thing. It's negative R. Does that make sense?
Yeah. Could we take the negative up and switch the
Yeah.
S1 and
So
S2?
yeah, the boundary of R is S2 minus S1. Absolutely. In fact, we could draw that picture. Let's draw S2 minus S1. There's S2. Right? S2 is oriented just like, there it is, S2. S1 is oriented inward like that, so that means that negative S1 is oriented outward. And so you're right. I mean, the boundary of R is S2 minus S1. But the problem asks to find something whose boundary was S1 minus S2, so we're going to leave the negative sign in there. Does that make sense? In other words, the problem specifically asks S1 minus S2, look at what I've got highlighted here. S1 minus S2 is the boundary of some solid region T. Describe the region T and note orientations as needed. So specifically, we're interested in S1 minus S2, not S2 minus S1. Cool? Okay. All righty. Okay, let's go on to the third one. Okay. Oops, I'm in my own way here. Let's see. There we go. All right, so let's see now. Okay, S1 is the part of the graph of this. Okay, yikes. Okay, we're going to have to go to some trouble here to figure out what this graph looks like, and you can play some games. Ask yourself, where is this function equal to 0? And let me just note first that this function here is equal to 0 whenever x is equal to 0.
Yeah.
Right? It's also equal to 0 anywhere x squared plus y squared is equal to 1. So, does that make sense?
It's negative 1.
Yeah, because if x squared plus y squared is equal to 1, then I claim this is equal to 0. Yeah, exactly. You could just rewrite this as x squared plus y squared equals 1. Yeah. Okay. So, all right. So let's try to draw a picture of this then. Now, of course, we're only interested in what's happening inside of the unit disk. So I'm going to try to draw the graph. Note it says graph. I'm trying to draw a graph of this function inside of the unit disk, and here it is. This is a tough picture. I never do a good job with this. It's just a little bit beyond my comfortable art skills, but we'll make do with what we get here. So there's the unit disk in the XY plane. And now this function that we're interested in, it's equal to 0 along this entire, wherever x squared plus y squared is equal to 1. So the function's 0 there. And we've already observed also that this function's equal to 0 whenever x is equal to 0. So the function's equal to 0 there. Is that all right? Okay. And what's it doing elsewhere? Well, oh gosh, let's see here. When x is positive, note, by the way, that 1 minus x squared minus y squared is always positive because we're looking where x squared plus y squared is less than 1. So that second factor is always positive. So if x is negative, the function's negative. If x is positive, the function's positive. So what we've got then is some little kind of hill thing. like that, sort of a little hill sticking up. Now, of course, it's 0 there, and it's 0 all along in here, but there's this kind of little hill sticking up. And then the function's negative over here, so it kind of goes down. It's not a very good picture, but it's kind of depressed down like that. Does that make sense?
Can you explain the reasoning again after?
Yeah. So over here, where x is positive, well, x is positive. I claim this is always positive because look at this. The x squared plus y squared is always less than 1, so this is always positive. So if x is positive 2, then the function's positive.
Right.
And that means it's kind of sticking up, like this here. And then when x is negative, the function's negative and sort of sticking down. Now this is really hard to kind of see, but let me take another angle on this. Let's look at this as seen from over here. So let's, as seen from over there. And as seen from over there, the x-axis is going that way, and the z-axis is going that way. And I claim that what's happening is the surface kind of bumps up over there, and it kind of bumps down over there. Again, that's as seen from this direction.
Right.
Does that make
why
sense?
are those curves a result of like?
Well, what I've got is a surface.
Are you treating y as a constant?
Well, I
Y
mean,
is 0?
yeah, maybe, yeah, sure. You could view this as where y is equal to 0. Maybe we're taking a cross section. Sure, let's say that. We're taking a cross section maybe through a plane, kind of like this. Just to help us sort of see what this is trying to represent. We're not going to do that much with this. Okay. So, all right. So there's our first surface. By the way, oriented upward. Let's remember that. So that little bit of surface there is oriented upward. Okay. Now, our second surface is the unit disk in the xy plane, which is just flat. Which is kind of like this, is just flat. There's what the unit disk in the xy plane would sort of look like, as seen from this angle over here. Does that make sense? That's what the unit disk is. I don't want to mess up my, well, maybe I'll draw it in green or something here. Let's see if I can. Okay, so now I want to draw S1 minus S2, and this is going to be a little hard, and I'm going to kind of cheat by using this little picture over here, this cross-section picture. S1 is this, right, upward-oriented thing. S2 is also upward-oriented unit disk, but then negative S2, this is S1, negative S2 is going to be downward oriented. All right, does that make sense? So we've got this downward oriented unit disk, that's the green here, and we've got this upward oriented weird surface that's kind of a little mountain there, and this little upward-oriented little hill, little depression, little valley down there. Good? And now here's what I want to appeal to your intuition and say that, between these two surfaces, there's a couple of different solid regions. On the one hand, there's let's see, what am I on with that?
Did you reverse the orientation of the unit disk?
Yeah, I did. That's why. So I wrote negative S2 here, because S2 goes up, so negative S2 is oriented down. So when I talk about S1 minus S2 as being the boundary of something, I can kind of sort of draw what it's the boundary of, and you can sort of see, we've got this little something there and this little kind of something in there. And we just have to be a little careful about how do we, what do we call these pieces and what orientations do we have to stick on them. So I'm going to give them names. Let me just call them like A and B, just to avoid confusion. So that's solid. Now that's a solid in there. I'm calling A. Again, this pen killing me here. That's A. And that's B. Cool. So, all right, well, now it's tempting to say A and B, but if you take the boundary of A, that's going to be outward oriented as it sort of should be, right? So I can say A here. Take the boundary of A, it's outward oriented, good, it's supposed to be outward oriented. But B is wrong, right? You take boundary of B, the boundary of B is outward oriented, it needs to be inward oriented just because that's the way these surfaces, S1 minus S2 happens to work out. And I think I have an extraneous little, I'm not sure how that little, that's weird. That's just supposed to be S1. I'm not sure what that is there. Sorry about that. I wish I had white out. Let me just cross it out. Yeah. So I'm going to say it's actually A minus B. Does that make sense?
Yeah.
So there you go.
So if A and B were the same sizes, then B would be the negative of A.
Well, no, now A and B are in totally different locations, right? A is this solid over here, kind of where X is positive. It's the sort of the little hill part. B is a solid that's way over here. Neither one's a negative of the other in terms of as domains. Now, we positively orient the A solid simply because we need its boundary to point in the direction that S1 minus S2 happens to point, right? And we negatively orient the B. Yeah, but you can't cancel and say that A minus B is equal to 0. They're totally different sets.
Right.
Does that make sense?
Yeah.
Yeah. Okay. So the answer to this question is, so S1 minus S2 is the boundary of this solid called A minus B, as shown in that picture there. And so it's hard to draw, but this is a good exercise in visualizing things three-dimensionally and thinking about, wait a second, which way does the normal go, and outward, inward, is this positive, negative oriented? It's just a good sort of geometric exercise, really. Yeah. Cool. Okay, let me stop. Oh, and that's time. Yeah, I better hustle.